Okay, good morning. So let us continue the lesson. Today the lesson is actually not very complicated at all. So that's the topic of second derivative and how we can use second derivatives, as I will teach you today, to determine the local extreme points. Again, we are back to local, not global. We are back to the local extreme points. So if you remember, in optimization problems and two previous sessions, we actually worked with global or absolute extreme points, but we want to go back now to local extreme points once more. Okay, so first of all, let me talk about the second derivative. How might be you are able to guess what is the second derivative? If I give you a function and you differentiate it once, you get a function. And now assume that this function is given to you from the beginning. You differentiate it once more, you get another function. This is called the second derivative of the first function. Yes? It's as simple as that. So let me just give you examples. So, and about the notations. So if I give you a function f of x, for example, let me write a very simple function for the time being. I give you this function, it's a polynomial, and then I know that definitely you can differentiate it. You differentiate it once and you show it f prime and you call it the first derivative, or just derivative here. So the answer is 15x squared plus 6x plus 2. Yes? And now, assume that this function is already given to you. You do this process, the process of differentiation once more. You get a new function. This new function is called the second derivative of the original function. As simple as that. And the symbol that you use, hopefully you can somehow guess, you just write f double prime. F double prime of x is 30x plus 6. So that is nothing, actually. And of course, even though the book has already talked about second derivative, but there is nothing to prevent us not to go further, yes? We can go to the third derivative, and then we can write this like that. But the main point today is just the second derivative, but I want to tell you that there is nothing to prevent us. So what is the third derivative? Here is just 30. And I can go to the fourth derivative. So the fourth derivative, it is not common to put these primes over and over again. So prime, double prime, and triple prime are common. And then if you want to go to 4, 5, 6, etc., you show it by a number on top. So you just write this. But then there is a matter of confusion between powers and this. To prevent that, this is conventional that you put a pair of brackets around that number. So whenever you see this doesn't mean f to power 4. This means the fourth derivative of the function. And it means that I give you a function, you differentiate it 4 times. And of course, this is clear. What happens here? 0. And then what will happen for the fifth derivative? 0. So actually you can say the nth derivative is 0 if n is greater than or equal to 4. N is a natural number. Yes? I just want you to know that we can talk about higher and higher order derivatives, but what we care in this lesson is just the second derivative. Yes, is that clear? And then let me also immediately tell you how we can write these things in Leibniz notation. It's a little bit weird. So if I give you y, the first derivative is just y prime. The second derivative is y double prime. The third derivative y triple prime. And after that we write y not to the power of n. The nth order derivative is just simple like that if n is greater than or equal to 4. And if I have the function form, this is the standard notation, but sometimes we can also talk about Leibniz notation. So do you remember, in Leibniz notation, instead of writing y prime, we write dy dx. Yes? But for the second derivative, it's a little bit more weird, you just write d, and then you put 2 here, as if it is a power, and then you put y here. But the interesting thing is that when you want to write the denominator, you have to put the power on top of x. So it has nothing to do with powers and things like that. That's just the symbol we use. For example, for the third derivative, what do? We just write this, and then we write the x to the power of 3. That's, I'm saying power, but that's not power. And so in general, yn, the nth order derivative, is nothing except this. So that's also in Leibniz notation if you want to express higher order derivatives. But you can also have the other. Do you remember another method for denoting the derivative? Do you remember what this D notation for capital D for derivative? Yes. Mm-hmm. So here, one way to show f prime of x is to say D acting on f of x. Here in this notation, when I want to talk about the second derivative, I also use the power notation. So this putting powers in pairs of brackets is only for this case and that case. In other cases, you just write second, this, and if you want to say, for example, f triple prime x, this is d to 3 to the 3 f of x. Somehow this notation is really related to the power, but we don't need to be worried about that. But don't worry, this is just notations. But the concept of the second derivative is very easy. Yes? Let me just give you some examples first to be able to calculate. This is a simple problem. If you already know how to differentiate, so you know how to differentiate 2 times. You know how to differentiate 3 times. So for example, let me give you this function, f of x equals to x squared square root of x, and then I ask you calculate f double prime of x, and I ask you sometimes calculate f double prime of a number, for example 4. So we want to answer these questions. Yeah, don't lock the door, please. Yeah. Thank you. So, I want to calculate the second derivative. The first thing that you have to do is definitely to do the first derivative. But to do the first derivative, because that's the product of 2 functions, and you haven't studied the product rule yet, and you will study it in Math 4 only, so you have to simplify it first. So before starting the differentiation process, so I would write x squared, and then this one, it becomes x to the power of 1/2. And then this becomes x to the power of 2 plus 1/2. And then it becomes x to the power of 5 over 2. Yes? And now I start differentiating it 2 times consecutively, one after the other. Yes? So the derivative of f, this is a very simple task to do. 5 over 2 goes down. And then you have x to the power of 5 over 2 minus 1. Then you really don't need to write all the details. You can do it in your head, and it's even better. So that is 5 over 2x to the power of 3/2. That's the first derivative. Now the second derivative, assume that, don't forget about the original function, consider this function is given to you from the beginning. So then what you have to do, you say that f double prime of x is the derivative of the first derivative. So it means that I need to, let me just write the details here. You don't need to. Okay, so then 5 over 2 is a constant, I pull it out, and then 3/2 goes down. And then I will have 3/2, 1 unit less. And then let us simplify. 5 times 3 is 15, 2 times 2 is 4, and then I have x to the power of 1/2. By the way, it becomes so simple that I prefer to put it back in the third sign, yes? And the form of the square root. So that is the second derivative. So what you are supposed to provide as one answer is, this is 15. It's 15 over 4 square root of x. And if I ask you what is f prime of f double prime of 4, it means you have to find the second derivative first and then replace x with the number. So from here, I can conclude that f double prime of 4 is equal to 15 over 4 multiplied by square root of 4. So I have replaced x with 4, yes? And then the square root of 4 is 2, and you multiply it here, so f double prime of 4 becomes just 15 over 2. So it's nothing very strange. Actually, it's very, very natural and straightforward. Yes? But of course, this might be just like a game, but why this is important to think about higher order derivatives. For the higher order derivatives, you have to wait why they are important. You can go and see in the university, okay? But for the second derivative, we can cook up a geometric argument. Yes, please?
Can you only do positive integers for
Pardon?
higher power derivatives?
I don't understand what you said.
Because like if you wrote n in brackets, what was that, n? Or what
Yeah, exactly, because it doesn't make sense. I cannot say that what is the 1.5 derivative, yes?
Yeah.
I should say the first derivative, the second
So
derivative.
it's only positive integers.
Positive integers. And by the way, that's good that you brought this up. There is also a convention. Some books, you see this symbol. This is called the zeroth order derivative. What does it mean, do you think? What is the meaning of? So this means when you write 1, it means you do the differentiation once. When you write 2, you do differentiation 2 times. So what was Aaron?
Maybe you don't differentiate.
So what is the meaning? It means that is the function itself. Yes? So you haven't done any differentiation. So that's good that you brought this up. So there is only one exception. 0 can also be seen in some books. And in that case, it means that we mean the same function.
So what's the point of writing f0?
There are some reasons, because sometimes you have to write formulas. So for example, that's a very famous formula for Taylor polynomial. So you can write this f of x equals to sigma, for example, and then you can write k here, 0, k factorial, and then x to power k, and then you will say k goes from 0 to infinity, for example. And then this is a good thing, because when people if they don't have this convention, they have to explain what they mean by that. But when we have this convention, if you are a mathematician and see this, you understand what does it mean. Yes, that's it. And on the other hand, it is natural, because when I write f0, it means that what is the function before doing any differentiation? So that's your function again, yes? Okay. Now, let us go to see what is the good point about even studying the second derivative here. Okay? And I want to be very specific about how this will help us to understand the behavior of the function regarding its local extreme points. Yes? That is a little bit delicate. I want you to understand it fully. But then, because I told you that there are many algorithms going on here, so I want you to understand, otherwise you will forget. Okay, so I want little by little talk about the second derivative test for the local extreme points, but that's not my purpose. So do you remember we have the first derivative test, and that is related to that sign table, yes? So you take the derivative, find the roots of the derivative, and you set up a table with the sign values positive or negative, and then you see that the function is increasing or decreasing, and then you realize which point, if any, is a local max, which point is local mean, and which one is a terrace point, yes? So more or less we want to do the same thing, but using the second derivative, and that is very important to understand, okay? So I want to ask you something. I want you to understand it yourself. So you see, I have this function. Let us consider this function for the time being. And this point is a local extreme point. We know that. Okay. And if I tell you before this point, so let me tell that this function is f of x. and then let me take this point A. So if I ask you if that is the local maximum point, if I ask you what is f prime of A, what is your answer? 0. Just review. Yeah, that's 0 because that's the horizontal tangent line there. So f prime at exactly A is 0. But then you know that on the left-hand side, the function is increasing, and then the right-hand side, the function is decreasing, and that is why the function is increasing here. What is the sign of the derivative? The sign of the derivative is positive. Why? Because no matter at which point I consider the tangent, yes, all these tangents are of this type. So the slope is positive. And when I pass and then I reach to the decreasing part, all these tangents that you have are of this type. So they are negative, yeah? So the derivative are negative. But of course, slopes are different. So this is a bigger positive number. When I reach here, it is still positive, but smaller. The slope is smaller. When I reach to here, it is still positive, but still smaller. That's fine. Okay, now let me ask you something. I define a function, so let us differentiate my function once, only once. Yes, it becomes a new function. And let me call this new function g of x. Yes? So what I have done, I have a function, I differentiate it, I don't want to understand the graph, forget about the graph. I get a function, so for example here you see, I had that function, it has a graph. Definitely the graph of this function is different from the graph of this function. If I ask you what is the graph of the first derivative, it is a parabola. But if I ask you what is the graph of this, it is not a parabola. So you see that the nature of the graph will change. But I call this new function a new function. Instead of giving it a name f prime, I give it a name g of x. Something like that. And now I want to ask you about this question. How g of x varies on this part? Yes, this I want you to understand. Yes, so for example, let me take this point here. So let me change my color. So here I consider this point. Okay, and then let me call this point, I don't know, for example, let me call it alpha. Yes? If I ask you what is g alpha, tell me g alpha is positive or negative, that's it. What is g alpha? This means instead of x I put alpha, so I have to put alpha here. So this becomes f prime alpha. Yes? But f prime alpha is the slope of the tangent line here, which I hope that you agree it is
Positive.
positive. Yes? And now let me go a little bit closer to this point and let me call it beta. So now let us try to be a little bit, so this is a little bit of that tangent line here, and then let me do a little bit of tangent line here as well, yes? Okay, now let me calculate g beta. So g beta is f prime of beta, still positive. But I want more than that. I want to compare the value of g alpha and g beta. Which one is greater, if any? Is there any good reason that we know which one is greater in this picture? Which one is greater than the other one? Yes?
G of alpha is greater.
G alpha is greater because it is steeper. Yes? The slope is bigger.
Yeah.
Okay, so this means that G alpha is bigger than G beta. Okay, what is the nice conclusion? Look, G of x, forget about what is f prime of x and just only concentrate on the function g. Now I am asking you, from here to here, I have moved to the right. What has happened to the function g? The g has decreased. Yes, because the value of g at the smaller point, at the smaller number, was larger than this one. So you see, alpha was less than beta, but g alpha is greater than g beta. Yes? Now I ask you one question. Is the function g on this interval from here to here increasing or decreasing? What is the meaning of the increasing and decreasing? Do you remember? An increasing function is a function like this. When I move to the right, the value becomes higher. This is increasing. Decreasing is like this. When I move to the right, the value becomes lower. Yes? Now, what is happening for g? By moving from alpha to the right, beta, the value of the function is decreasing, is going down, because g beta is smaller than g alpha. Yes?
Should you conclude that g starts from positive infinity and goes to 0?
No, don't get confused with these things. Just answer my question. From here to here, the function is increasing or decreasing? G function. If I ask you about f, this is easy to answer, because you have the graph of f in front of your eyes. From here to here, f is increasing or decreasing? When I go from here to here, the height of the function is going up. So the function itself is still increasing, but the function g is decreasing. Is that understandable? Yes or no? Because alpha is smaller than beta, but suddenly g alpha becomes greater than g beta. So it means that when I move from alpha to beta, the value of g beta is smaller than the value of g alpha. So the value of g has gone down. Is that understandable? Yes?
Because it's a slope.
Yeah, exactly. But I want to understand something else. I want you to understand g is decreasing. Is that understandable? Yes? By going from alpha to beta, the value of g, so alpha is smaller than beta, but the value of g at alpha is larger than the value of g at beta. So it means g is decreasing. Yes? Yes or no? Okay. So when you say that a function is decreasing, it means that this first derivative of g is what? Positive or negative?
Positive.
No. The function is decreasing. That was a very... If a function is decreasing, what is the derivative? Positive or negative? Negative. So the derivative of g is negative. Yes? So we learned that on the left-hand side, so we know that f prime of a is 0, but on the left-hand side, we learned that f is increasing. Be careful. When you say f is increasing, it means that f prime of x is positive. But we learned that g prime of x is negative. Yes? If you have already learned your lesson, you don't need to be worried about this at all. This is the new lesson. This is the old lesson. Yes? Now let us go on the other side. Let us see what happens here. You can immediately predict, based on your previous knowledge, what is f prime of x when I go to the right? What happens for the derivative, positive or negative? At this point it is 0, but what happens here? Negative. Why? Because we learned whenever the function is decreasing, its derivative is negative. Yes. But let us see what happens here. This time, let me consider two other points. I don't know. Let me call one of them point alpha, beta, gamma, and, for example, theta. If I go here, and if I go here. Here, the tangent is like this. here the tangent is like this. So now I want to ask you the same question. I want to write g prime of x here and predict if it is positive or negative by more or less the same way of reasoning. So what do you think will happen? Here, the slope is this one. Of course, the slope is negative. But when I go forward, the slope is still negative, as we of course, that is we expect. But is it bigger or smaller? Is it, so here, it is steeper, and here, it's not that steep. So which one is bigger? But be careful, these numbers are negative. Yes?
Is it also getting smaller? Is it decreasing?
So which one is bigger? Can you tell me? So here,
The first one is
gamma,
bigger.
here gamma
Yeah, gamma's bigger.
is less than theta. What can you predict about g of gamma and g of theta?
G of theta is bigger.
So here, this number is so here this number is actually
Greater.
this is more negative. Yes. So this is less negative. So this one is bigger. Yes. So
Which one
less
is bigger?
negative means bigger.
Okay.
Yes.
Yeah.
Because if you have -3 and -2, this is more negative. This is less negative. So which one is bigger? -2 is bigger.
Yeah.
Yes. So when this is more negative, this is less negative. So this one is bigger. So g theta is bigger than g gamma. Yes. Am I right or I'm confused myself? So let me see.
No.
Is that right?
G of gamma is bigger, I think. Because G of theta is more negative.
Yes, yes. G of gamma is bigger, yes?
Yeah.
Yeah, that's right. Thank you. Okay, so now tell me, what is the conclusion? Is G increasing or decreasing? You are going to the right, but the value of G on the left is greater than the value of G on the right. So what's happening? It's G, yeah?
It's decreasing.
Decreasing again.
Yeah.
So it does. You see, it is interesting. If you look at this function, the derivative of f, one side it is positive, one side it is negative. But when you look at the derivative of g, it remains negative on both sides. Yes. But that is very nice. Why? Because this is the first derivative of g. But can you tell me what is the first derivative of g according to this equation now? If I ask you what is the first derivative of g, g is the first derivative of f, so it means that you take another derivative of f, yes? Because g, assume g is the first derivative of f. Now I talked about the first derivative of g. But the first derivative of g is the second derivative of f.
Yeah.
So this becomes the second derivative of f. Yes? So this function, the second derivative is negative on the left and on the right. So we find a nice criterion, yes? This is negative. So g prime of x, when I have a local maximum point, the second derivative should be negative. Yes? Is that understandable? Yes or no?
Yeah.
So why do you suspect Abdullah?
I didn't just understand the last part when you said the second one is.
No. Do you realize that g prime should be negative on both sides? Yes? And g of x is f of x. So what is g prime of x?
Double F.
It is double f. So g prime of x is negative, and I am looking at a maximum. G prime of x is negative. G prime of x is equal to this. So f prime, double prime should be negative. So this means that when I am looking at the maximum point, the second derivative should be negative. Of course, because the next part the book has skipped because they have kept this for they have kept that for interested students. To be really clear, I want to say that where the second derivative is negative, you need to have this way of thinking. So you have an upside down bowl. You know, it's called concave. Okay, so here the second derivative is negative means that if the second, I don't want to repeat this argument, but you hopefully if you want to understand it better, you can just repeat the same process again, but for a local minimum. You will realize that this will always be positive this time. Yes? So this means that if the second derivative is negative, I am facing this scenario, which is called concave. I want you just to know the words. So it means that the function, so if I want to give you the meaning of the concave, a function is called concave at a point if I draw the tangent and the graph is below that tangent line. So then I would say that the graph is concave. And if the graph is above the tangent line at that point, then we say that the graph of the function is convex at that point. So what I want you to understand is this. I want you to understand, if I use the first derivative, I can detect the local extreme point. How? By looking at the sign of the first derivative. If it is positive on the left and it becomes negative on the right, then it means that point is a local maximum point. If this is the other way around, this is negative first and then positive, then it is a local minimum. This is for the first derivative. But you can also detect the same kind of behavior using the second derivative rather than the first derivative. Yes? So in that case, you take the second derivative at that point of interest. If it turns out that the second derivative is negative, it means that you are facing this situation. It means that you are looking at a maximum. If the second derivative turns out to be positive, you will be facing this situation, and this means that the function, that point is actually a local minimum. Yes? Is that understandable? So that is the content of the second derivative test. And I will write it as an algorithm, but I want you to understand the geometry. I want to give you time a little bit to digest this. Is there something part that you don't understand? Yes or no? Okay. So what is the point? The point is that for a local maximum, you can detect this in two different ways. One way is using the first derivative, which already we did, and second, using the second derivative. Yes? Is that clear? For the second derivative, if the second derivative at the point is negative, you are looking at a maximum. If the second derivative at that point is positive, you are looking at a minimum. And then unfortunately, there is a bad side about it. If you are unlucky, it might happen that the second derivative turns out to be 0, which is neither positive nor negative. So it means that you have wasted all your time. You have to go back and do the first derivative test. But I really recommend you to learn the second derivative test, because at the functions that you are working in matrices, sometimes it is really, really faster. Yes?
I don't want to confuse the class, but you can answer if it's appropriate. Can we compare f of alpha and f of beta if the graph is the graph of derivative of f? I mean, the graph is the graph of derivative of f.
Yes.
And can we compare then the value of f of alpha and f of beta?
Not really. going backward is probably not that easy. Yes? So you are asking that instead of writing this as the graph of the function f, I write it as f prime of f.
Yes.
F prime of x. And then what do you want to ask? You
Uh,
want to ask about...
compare the value of f of alpha and f of beta.
No, that's what I am saying is probably not. Because if that is f prime rather than f, yes, then by this picture I see that f prime of alpha is smaller than f prime of beta, yes? And then your question is that, can I go and conclude something about the relation between f alpha and f beta? So in principle, somehow you're asking, can I integrate this inequality to get a specific one? I don't think that's a straightforward question, but I need to think about it. Yes, that is not very trivial, that if the derivative of a function is smaller than the derivative, if the derivative of a function at a point is smaller than the derivative of the function at another point, can we say that f alpha might be, we can make up some examples, yes? So for example, if I give you this function, f of x equals to x squared, yes? And then the derivative becomes what? 2x. And then let me calculate f prime of minus 1. This becomes minus 2. And then I calculate f prime of minus 2. It becomes minus 4, yes? Now which one is smaller? F prime of minus 2 is smaller than f prime of minus 1. Is that right?
Yep.
But then, if I ask you what is f prime of what is f of minus 2 is 4. What is f of minus 1 is 1. So which one is bigger? So we had a function so that f prime of minus 2 was smaller than f prime of minus 1, and f of minus 2 is larger than f of minus 1, yes? But I can make probably another example, for example, f of x to be x cubed, and then you can differentiate it, yes? Let us see how it works. So f prime of x is 3x squared, and then if I write f prime of minus 1, it is 3, f prime of what? Minus 2 is 12. So which one is bigger? F prime of minus 2. So f prime of minus 1 is smaller than f prime of minus 2, yes? But if I ask you what is f of minus 1 and f of minus 2, then f of minus 1 becomes what?
Minus 1.
Because minus 1, f of minus 2 becomes minus 8. Which one is bigger now?
F of minus 2.
So it means that both scenarios can happen, yes? So f of minus 2 is smaller than f of minus 1, yes? Is that the same thing?
I think it's the same.
Yeah, it is the same, yes, because the conclusion is f prime of minus 2, f prime of minus 1. Then this was flipped, and now this one is flipped as well, yes?
Yes.
So that's not probably, yeah. Might be I can come up with some examples that it violates this, I have to think about it. But I don't see any general rule for that, yes?
But if you have parabola, then we can claim that.
So what you are saying is that the slope of a function at a point is smaller than the slope of the function at the other point, yes?
Yeah.
Might be the graph is easier to understand, yes? Can we understand? So when you say f prime of alpha, of course definitely not, yes? So let me just say f prime of alpha is, so the slope at alpha is smaller than the slope at beta.
Yeah.
So for example, like this. Yes?
Yeah.
So this point, yes. Yeah, this slope here is smaller than the slope there. Yes? But f of alpha is also smaller than f of beta. Yes? But what happens if I consider the other scenario? Yes? So I want to
But I
make
mean,
it
if you have parabola,
so
like,
not
graph-
parabola, so you can just go here and then go down and then go here, yes?
Yeah.
Okay, so here this one is still smaller than that one from slope point of view, but this one is lower. So it's possible. So both cases are possible, even though my example was not a good example. Yes? Is that understandable? So,
yeah, but I mean, if the derivative of f is a parabola,
yes?
then we can conclude that value of f of alpha is bigger than value of f of beta.
I'm not sure about that, because if I want to say something, it means that I have to have the proof for
Yeah,
that.
I know.
Yes?
We can take it
But at least
later.
in this example, it shows that f prime alpha is smaller than f prime beta, but f beta is large. In this case, I have tried to make this steeper, so f prime here is larger than the f prime here, but this one is lower.
Yeah.
So there can be possibilities, but now you are talking about if I have a parabola, this can happen or not. We can think about it. Okay, any questions regarding this? Now let me go back and then try to give you some examples. Okay, I just wanted to tell you, I forgot to say, if you are unlucky, and I told you that if the second derivative also turns out to be 0, because the first derivative is already 0. If the second derivative is negative, that point is related to a max. If it is negative, if it is positive, it is related to a mean. But if in some cases you get unfortunate and it becomes 0 again, in that case it is not inclusive. Everything can happen. Yes, I can give you examples why this is the case, and then we can start working it out. Okay, so let me tell you something, and then I will write it formally here. So let me ask you this question. I give you a function f of x, x to the power of 4. You need to trust me on that. If you draw this, it is like a parabola a little bit steeper. That would be y equals to x. Yes? Let me concentrate here. If I ask you this point, what this point is for this function, it is easy to see that this is a local minimum. Yes? And now, if I take the first derivative, it becomes 4x to the power of 3. If I take the second derivative, it becomes 12x squared. If I put the derivative at 0, it becomes 0. If I calculate the second derivative at 0, it also becomes 0. So you see, this point is a minimum point, but f prime and f double prime at that point are both equal to 0. So it means that if the second derivative is 0, above that the first derivative is 0, it might happen that this is a minimum. So it is possible. Now consider another function, g of x equals to negative x to the 4. Then what happens if you draw the graph of that function? This would be something like that. And then again, let us look here. What is the type of this point? It is a maximum. But let us calculate g prime of x, which is minus 4x cubed. And then let me calculate g prime of 0, which is 0. And let me calculate f double prime of x. It is minus 12x squared. And what is g double prime of 0? Again, 0. So I gave you a function whose first and second derivatives are both 0, and I have a minimum. I gave you another function whose the first and the second derivatives are again 0. I have a maximum. And then I can give you another function h of x to be x cubed. Yes? And then I have this function. If I draw this function, the graph of this function would be this. So if I ask you what this point is, you will say that this is a terrace point. Yes? And then let me calculate h prime of x again. It becomes 3x squared. And I calculate h prime of 0, it is 0. And I calculate h double prime of x, it becomes 6x. and let me calculate h double prime 0, it is again 0. So here you see on the board very, very simple functions, 3 different functions. For all cases, the first and the second derivatives are 0, you see. But in one of them, I am facing a minimum. In one of them, I am facing a maximum. And in another one, I am facing a test point. So that is really unfortunate. So if the second derivative above the first derivative turns out to be 0, you really don't know which situation you are facing. Then it means that you really have to go back and use the first derivative test to detect the nature of that particular point. Is that understandable?
But if you continue, say f a third prime of x and then f fourth prime of x, you will end up with a constant number somewhere.
In this case, yes, but
Yeah.
not generally. If your function is a polynomial function, yes, after a while you get a 0 at the end. A constant, and after that a 0. But for example, if you have a sine function, sine x, cosine x, if you differentiate them, sine becomes cosine, cosines become sine. And they will never be a constant. They will interchange to each other. That's not in general true. And that's not, by the way, the point of this problem. The point of this problem is that in the second derivative, if you get the second derivative also equal to 0, because you don't have the graph in front of you, then you don't know what to conclude, because either one of them can be possible, potentially, yes? But which one is which, you have to go back and do it using the first derivative test, yes? Okay, so let me do some exercises from the book. Okay, so let me formalize it for you here, so if you want, you can have it, okay? The second derivative test, let me write it here informally, but in a summarized form. So this is the second derivative test. Okay, so for example, a function f is given to you. What you do, the first step, you differentiate it. So let me write. Determine f prime of x. Number 2, again, you have to put f prime of x equal to 0. Yes? And let A be a solution. Yes? Number 3, you determine f double prime. Number 4, okay. If f double prime of that number A that I found here is positive, then the point A and f of A is a local minimum. If f double prime of A turns out to be negative, then the point is a local maximum. And then, unfortunately, if f double prime of A turns out to be 0, the test is not inclusive, they say. Then the test, I would say, is silent. You cannot draw any conclusions out of it. So that is the algorithm that you should have in mind if you want to use the second derivative test. And then you need to know that there is one exception here. But in the first derivative test, there are no exceptions. It always works. Yes? But for the second derivative test, if you get unlucky, you have to... Of course, you don't have to redo everything, because in the first derivative test, you do this part and that part as well. But the second part, you don't need to do. Okay, so if you don't mind, let me solve some problems from the book, and the lesson is finalized here. So let me move this up. Yes. Because usually you are facing with polynomial functions, so the second derivative test, I would say, is easier to work with. Yes. So there are some functions in the book. I just want to write them down and use it for you. Okay, so it is exercise 3052. Exponent 3. C. Okay, so here a function is given to you. Yes, you are supposed, in the problem, by the way, they have asked you to use the second derivative to answer the question. So in those questions, if you do the first derivative test and if it is correct, you don't get the points. So you have to respect what is wanted. So part A, this function is given to you. F of x is equal to x to the power of 3 minus 3x squared minus 9x plus 7. So what is the question? The question is, use the second derivative test, they have emphasized on that, to determine the local extreme points of this function and their natures. So it means that if they are max or if they are min, yes? So if you want to follow the algorithm somehow, so you see these algorithms are getting very similar to each other. So if you don't learn, you get confused. So you need to understand what's going on. Okay. The first thing that I do for this function, I take the derivative, I differentiate it, so it becomes 3x squared minus 6x minus 9, and then I equate it to 0 to find my candidates. So if I put it equal to 0, this tells me that 3x squared minus 6x minus 9 is equal to 0. Everything is divisible by 3, so let us just do division. X squared minus 2x minus 3. You can use ABC formula, but I think now you should be comfortable with factorization. Yes, here. So you factorize it. I ask myself, I need two numbers whose sum is this and the product is this. What are they? Minus 3 and positive 1. Yes. Of course, you can use ABC formula. And then there are two candidates that you get. One of them is 3. And the other one is minus 1. So these are my candidates. They might be max, min, 1 max, 1 min, or terrace. We don't know yet. So let me remind you, if I wanted to use the previous method, do you remember what I'm supposed to do? The previous method means the first derivative test, yes?
You put those x's into the original function?
No. In general, I have to set up that long table, yes?
Oh, the sine table.
Sine table. So it means that I have to spend quite time to write it down. But the good point about the second derivative test, I don't go through that method. I just do one more derivative. Okay, be careful, not from the simplified version. Just from the original function. That's important, yes? So I take the second derivative, it becomes 6x minus 6. And then what I need to do is just to put these numbers into the second derivative and see if it is positive or negative. Yes? So I calculate f double prime of minus 1. It becomes 6 times minus 1 minus 6. It becomes minus 12, negative. When it is negative, I conclude that minus 1 and f of minus 1 is a local maximum. According to what I have written, you see there, this is the second line. If f double prime of a becomes negative, then a and f of a is a local maximum. But you shouldn't write it like this in the exam. You need to calculate f minus 1 for me. So it means that I go back to my original function. If you want, you can go to scratch paper and calculate this number. What is f of minus 1? I have to put minus 1 here. Minus 1 minus 3 is minus 4, plus 9 is 5, and 12. So this means that I have minus 1 and 12 is a local maximum. And now I calculate the second one. F double prime of of 3. Don't get confused. This is F double prime. So you go to your F double prime, replace x with 3. So this becomes 6 times 3 minus 6, which is 12. And this time it is positive. So what is the conclusion according to this algorithm? So this tells you that 3 and f of 3 is a local minimum. Yes? And of course you have to calculate this number by plugging it in. 3 to the power of 3 is 27, with that one is gone. It is minus 27, so it's minus 20, yes? So this means that this point is 3 and minus 20. I would say this is simpler, isn't it? If you, instead of drawing that table and things like that, you just calculate the second derivative. But of course, if your function originally is complicated, the first derivative becomes more complicated, and the second derivative becomes even more complicated. So this is why sometimes you really want to do the first derivative test. But for the functions that you face in Math 3C, that is a really good option. Yes? Is that clear? Yeah. Okay, let me solve the other problem, 30.53, as the last example for today. So let me clean this part. Okay, so the function given to us, hopefully this is one of those exceptions. Let us see. Problem 30.53. Again, the same question. With the help of the second derivative, determine the local extreme points for this function. Okay, so what I have to do, I have to differentiate my function first time. So it becomes 4x to the 3 minus 12x squared minus 16x. Then I equate it to 0 to get my candidates. This becomes this function. Okay, and this is a third degree polynomial, so if I want to succeed to solve it, I have to be able to factorize it. But factorization is very simple. Here I just take 4x out. This becomes x squared minus 3x and minus 4 equals to 0. Okay, I get 3 candidates, yes? Okay, if you want, I can factorize it more. 4x. Hopefully you know how to factorize. You don't need to factorize. If you don't like it, you can just use ABC formula to find the roots. But let me put 2 x's here. I ask myself, I need 2 numbers whose sum is negative 3 and the product is minus 4. Guessing these numbers are very simple, so it becomes minus 4 and positive 1. Yes? So this means that there are 3 candidates. Either x is 0, or x is 4, or x is negative 1. But these are just candidates. There is no guarantee if they are mixed local extreme point or not. But then if they have asked you to use second derivative, if they haven't used this phrase to force you, that's up to you which one you want to choose. But if they have explicitly mentioned use this test, you have to follow the instructions. So here, I take another derivative. What happens? It becomes, I go back to my function, differentiate it once more. Be careful, don't go to the simplified version. You need to go to the original derivative. So this becomes 12x squared minus 24x minus 16. And be careful, you really don't need to find the exact value. Because you just need to convince yourself if it is positive or negative. If you are convinced, that is it. You really don't need to get the exact value. For example, if I ask you what is f double prime of 0, the answer is simple. You can get minus 16, it's negative. So this means that 0 and f of 0 is a local extreme, a local maximum. But of course, you shouldn't write f of 0 in the exam for me. You have to calculate f of 0 as well. But that is simple. You go to your original function, replace x with 0, you get 0. Yes? So this means that this point is nothing except the origin. So the origin is a local maximum point for this function. Yes?
How did you just put in f double prime of 0 instead of negative 16?
Instead of x, I put 0.
Well, why?
Or f double prime of 0 means x is 0.
Oh, sorry.
Yes?
Yeah.
So, and then I go f prime of 4. F double prime of 4, sorry. So it means that I have to go to the second derivative which you see on the board and replace x with 4 this time. So then it becomes 12 times 4 to the power of 2, 24 times 4 minus 16. You really don't need to calculate the exact value. Of course, exact value is the best choice, but you want to convince yourself if it is positive or negative, yes? I think it's positive, yes, because this is 16 times 12 is what? How much? Is 192.
We can say that a function cannot have 3 maximum points. I mean,
Not this function, but in principle we can have 3 maximum points,
Yeah,
but
but-
not for the 4th degree function.
yeah, but only 3. Well, only maximum points. I mean, here
but-
we have only maximum points if f.
No, we should
Double
also
prime of
calculate
4.
the other one. How did you calculate the other one? Yes, because 2 of them should be of one kind, and the other one should be of the other kind. Yes,
Yeah.
we haven't calculated the third one. What you're saying is that we either have 2 max, 1 min, and the other, or the other way around.
Yeah.
Yes.
Yes.
Yeah. But anyway, that argument is not acceptable, even if it's correct. You have to follow the
But
arguments,
In this question,
even in this question,
why not?
because that is something that you make it up by intuition. That's not mathematics, unless you have a proof for that.
But how can you have 3
No,
local
this how, you cannot say how, because it might happen there is an artificial function that I don't know, but it has that property. And I don't understand your question. Just tell me once.
It's not a
more.
question.
What?
Yeah, I just guess. I
No,
guess.
just tell me again. Might be I have confused myself because I understand it wrong. So you say that I don't need to calculate anything right now?
Yes. It has to be a local minimum point.
Here?
Yes.
Why?
Because we cannot have 3 local maximum points.
No, but we can have 2 max and 1 min, or the other way around.
Yes.
We have 3 candidates. How do you know that this one is the one that you want?
Because I calculated f of.
Okay, you calculated that
yeah,
one. I
yeah.
haven't reached that step yet.
Yes, sorry.
Yeah. Yeah.
Because I calculated f double prime of -1.
But even in that case, don't do that in the exam, especially in the national exam, because these are polynomials, they are well-behaved functions, so we know that this cannot happen.
Yeah.
But we don't know for all possible functions this cannot happen.
It's a rational argument.
I don't call it rational. For me, it's very, very hard to take these steps, because when you say that's always the case, it means that I have looked at all the functions. So it might be the function is not continuous.
Yeah.
Because you are thinking about the continuous
Yeah, but
functions.
in this question, it's a polynomial.
Yeah, in that,
Then-
I'm saying that this is in this question is right,
Yeah.
and I don't like this kind of arguments. Yes,
Yeah, okay.
you need to give me an argument according to mathematics. This argument will also work if the function is not continuous. Yes, but you are saying that for a continuous function, I can have another theorem. Yes, you can prove it and then use it,
Yeah.
but we haven't that proof yet.
Yeah.
Yes. Okay, but anyway, even if I want to use your method, this is not still clear because I have 3 points, yes?
Yeah.
So this becomes 100 what, 92, this is, yeah, that is positive. If you want, you can calculate the exact value. So this means that 4 and f of 4 is a local what?
Min.
Min. And then if you don't mind, you can put yourself this into the function and calculate the number. That is easy. You have to raise it to power 4. Of course, this power 4 and this one is gone. This is 16 times 8. What's that? 128. So it's minus 128. And then you calculate f double prime of minus 1. Now might be what Benjamin said is right here because oh, by the way, this is also not clear. If I calculate it
No,
in
I
this
first
order,
calculated
that was
minus
lucky.
1 and 0
Yeah,
and
yeah.
then.
That's why.
concluded.
But here I cannot draw any
No, no.
conclusions because the order that I have chosen is 0, 4, and minus
Yes,
1.
you're right.
So if I put minus 1 in the function, it becomes 12 times minus 1 to power 2 minus 24 times minus 1 and minus 16. What's the answer? Positive or negative? This is positive. This is positive, so definitely it becomes positive. Yes? So this means that minus 1 and f of minus 1 is a local what again? Minimum. So finally this function has 2 local minima and 1 local maximum. Yes? And of course you have to calculate f of minus 1 by putting it back into this function, and that is also easy. Let me just write it here for you. If I put minus 1 here, it becomes 1 plus 4 minus 8, so it is minus.
It's negative, I think.
Is it?
It's negative.
Is it negative?
Yeah, it's negative.
Minus 1 times 24, and this is positive. I put minus 1 here,
Yes.
so this becomes positive,
Yes, 12.
12.
Minus.
And then
24.
minus 24 times minus 1 is positive,
Yeah, yeah.
and it becomes positive again.
Yeah, you're right.
Yes?
Yes, sir.
So this becomes a local minimum. And if I put minus 1 here, it becomes 1, 4 minus 8, it is minus 3. So it is minus 1 and minus 3. So I really recommend you, if you want to appreciate the difference, I want you to do this using the first derivative test at home as well, and then compare the results. You should be able to get the same conclusions from the first derivative test as well. Okay, any questions? Okay, I will try to update the Google Classroom so that you know which topic you are supposed to work. And then you see that in the book, another section is only for interested students, so for the time being I will skip them. And then the next part is usually using GeoGebra. Yes? So using GeoGebra to discover something, but there is one important section left, and that is the derivative of exponential functions, which we haven't studied yet, and that would be the last section of this chapter. So more or less we are coming to an end, but of course for the exponential function we have to do a lot of things. So definitely the exam would be somewhere after the break, okay? Not before the break, but we will decide it together. Thank you very much.
Du sa det.